This video is going to examine some basic laboratory procedures in hemostasis and coagulation labs. And the goals of the video, hopefully what you'll be able to do when we're all done here, be able to recognize that hemostatic tests fall into 4 distinct categories and state the category names. We will look at a handful of different lab tests, and for each of those, I'd like you to be able to state the aspect of the coagulation that it measures. So basically of those 4 categories, which one of them is measured by a particular test. Describe the reagents and the test procedure, so what you need and how it's done. And then state normal values and interpret abnormal test results. What could that mean about our patient's health status? And then kind of a subtype of the lab test, we're going to discuss something called INR, state its purpose, and calculate the INR for a patient on anticoagulant therapy. So looking at the first objective, the types of hemostasis and coagulation tests, remember that hemostasis means blood stopping, essentially, and coagulation is one of the processes that we have to help stop blood loss. So when something's wrong with this mechanism, we kind of have 4 places we need to look to figure out what's going wrong. And one of the first areas that we want to examine is maybe the bleeding problem is coming from the blood vessels themselves. Perhaps the blood vessels structurally are not okay, or something's going on, the capillaries are not able to retain the fluid like they are supposed to. So we have lab tests that will check to see if this is a problem. Maybe something's up with the platelets. Maybe we have too many, maybe we have too few, maybe they're being taken out of circulation, maybe something's wrong with them structurally. We have lab tests that will help us look at this. You should be familiar with some of that in lab when we did the platelet count, or when we do the platelet count. Then you have to look at, okay, what about the coagulation cascade, that big fancy series of proteins that ends in forming a true fibrin clot? There's lots of potential for things to go wrong here. We have many lab tests that will help us figure out if this is a potential issue. And then lastly, we have the fibrinolytic system, which is actually the system that works opposite all the others. Basically, fibrinolysis says, all right, we made the clot, we healed the damage, now we need to get rid of the blood clot. You don't want to always have a blockage or stoppage in blood flow. So fibrinolysis could be an issue if we're not able to remove clots like we're supposed to, or if we are not able to clean up like we need to in order to restore blood flow. So maybe this is a potential area that could go wrong. All of these we need to examine to really narrow down what might be going on in a patient. So one of the first tests we'll talk about, and perhaps the most archaic, is called bleeding time, and it is pretty much just like it sounds. This is a test that is going to kind of check to see, are your platelets working and do you have enough of them, and then are your capillaries working? And so it's measuring essentially how long does it take you to stop bleeding, because remember the very first stoppage of bleeding tends to happen by the platelets sticking to the site of damage. So what you do is you will basically cause a little bit of damage to the arm of the patient. Again, it doesn't sound so great, but it's just like a finger prick. You can kind of see here that there's a blood pressure cuff that's on, putting some pressure on the arm, and then they use a very similar to the little finger pokers. They'll put it on the arm and cause a little nick, and then essentially time how long it takes for the blood to stop bleeding, or the arm to stop bleeding, and they'll blot it away. You can see the filter paper in the bottom right corner, kind of picking up the blood as it's coming out, and you have a timer so you can sort of see like how long did it actually take them to stop bleeding. And this kind of gives us an idea of perhaps capillary fragility, as well as if the platelets are there, if this is elongated, so if it takes longer than normal. Again, kind of archaic, but it really does get the job done. Platelet count is another way to check to make sure that our platelets are present, and we have done that in labs, so I won't talk about it here. Make sure that you review it and keep it in mind when we talk about these hemostasis type tests. Another type of test we do to measure the functionality of platelets and also the presence of some other factors in the blood are called platelet closure times. So what happens in your body, you can see this says in vivo hemostasis, you have some damage that happens to the lining of the blood vessel wall, and the collagen that's exposed from the endothelial cells and from the underlying connective tissue will stimulate a stickiness in the platelets. And so the platelets clump and they close the gap and then hopefully stop the bleeding. And that's due to the presence of collagen fibers. So what we want to do in a platelet closure time is we want to see how long does it take that to happen. And we want to do it in an in vitro setting. So you kind of have a similar situation here with this PFA 100 is a type of machine that does this kind of test. And we'll talk about how that works in just a second, but you can sort of see the idea is similar. You're just trying to stimulate platelet clumping and measure how long it's going to take for that fluid to stop flowing, or in this case, the reagents to kind of stop moving. So basically what happens in a platelet closure time test is you have a very, very small aperture. An aperture is just a really little hole. And you can kind of see that on the image to the right, just that little hole between the two green boxes. What will happen is you have this sample. So you'll have plasma, in this case you do have some red cells as well, that you've collected from the patient. You flow it through the machine and it goes through this little aperture, this hole, and aligning on the opposite side of this hole are things that will stimulate clumping. So you see that collagen coating, or it says epinephrine or ADP. Those all, when platelets get to it, if they function correctly, we have enough and the other factors are present in the bloodstream, then they will start to clump. This initiates the clotting, and then what happens is the fluid, as the platelet clot is building up, the fluid that's normally flowing through this little hole eventually stops, right? Because the platelets have closed the gap. And so as a result, we can measure that stoppage time. How long does it take the hole to actually close in order to, if the platelets are working? And if you have enough and if everything's working fine, it'll take X amount of time. But if you're missing them, or you're missing a protein or something like that, there's another issue, then this will obviously take a little longer than normal. So this is looking at how long does it take platelets to close a gap when it is present in the bloodstream or in tissue damage somewhere. Platelet aggregation is another somewhat similar test, obviously looking at platelet function here. It's not so much how long it takes them to clump, but that they are able to clump, because platelets can lose that functionality, and when they lose that, then they're not really functioning, they're not doing their job, right? So blood won't stop flowing. And typically, platelets should change shape, get stickier, and clump together when they're activated. So in the presence of collagen, that ADP or epinephrine, that should make them active, sticky, stopping the blood loss that's happening. What we'll do in a platelet ag study is you will remove what's called platelet-rich plasma. So this is plasma that has that buffy coat in it. And you will basically be looking at how light is shining through it and how that changes as platelets clump. So you have on the left PPP, which is platelet poor plasma. So that's just plasma without the buffy coat. And then PRP, which is platelet-rich plasma that has basically a well-distributed amount of platelets throughout it, right? So we use the platelet poor plasma to act as a blank, like what does it look like, how much light goes through plasma when there are 0 platelets, and then platelet-rich plasma, we check to see how much light is going through, and you can actually see those little orange arrows on the left of the PRP, it's bigger, and then on the right it's smaller, and that's showing that there's just so many particles in the solution that as the light is flowing through, it's getting hit and it's not transmitting all the way across. So we'll use kind of like a spectrophotometer, turbidimeter kind of machine to read this. So what will happen next is you'll take the platelet-rich plasma, and again, remember it's kind of homogeneous. It's been mixed up, so everything's just floating around pretty evenly, but that's causing light scattering and such. And you add what's called an agonist. And an agonist is basically going to trigger clumping of the platelets. So it's some sort of chemical that will get the platelets to become active and clump. And if they are functioning correctly, they will form pretty large visible clumps, and then what will be left behind is kind of a clearer plasma, right? So all those little things that were evenly distributed, all of a sudden it's not evenly distributed because they're forming big clumps and potentially just falling out of the solution. So they leave behind this kind of clear fluid. The light transmittance aggregometry will measure how much light is now able to go through. So if all the platelets clump and fall to the bottom, then you should have something almost as able to let light through as the blank, the platelet poor plasma. So that's ideally kind of what we want. We want those platelets to work, and when they're working, they stick together, and in this situation, they fall out of solution. If they all stay homogenized in the solution, that's a sign that they're not able to be triggered and activated. So it's a little bit indicative that something is functionally wrong with the platelets. This image sort of shows the difference. So the picture on the left is going to be the platelet-rich plasma where they're all sort of even. And imagine trying to shine light through that. Not a lot's going to get through because there's a lot of particles in there. Versus on the right, because the particles have become bigger, there's more gaps, clear gaps for light to get through. And so when you shine light through it, more light is going to make it to the other side. And that's sort of what this picture here is showing. On the left, the baseline light transmittance in the platelet-rich plasma, a lot of little things that are suspended blocking light from getting through. The detector notices there's not a lot of light. And then on the right side, you add the agonist. The clumps form, so there's more gaps. The light can go through. The detector can recognize that there is light. And so we can kind of get a read on how much clumping is happening. And we have a known range. It should be about this much. And when it deviates from that, too high, too little, whatever, then we can maybe start to piece together what might be happening with the patient's platelets in their body if they're having some sort of hemostatic issue. So this is platelet aggregometry, aggregating, clumping, kind of lumping together. So now we're going to look at some tests that are going to examine coagulation cascades. And we're looking primarily, obviously, at these. We've seen these in lab, or you may have seen these before somewhere. Basically, the series of events that have to happen in order for a clot to form. And you can kind of see there's an intrinsic pathway where you have this sort of internal surface contact damage that will trigger this pathway. And then extrinsic, remember, is triggered by some sort of external sort of physical tissue damage. So both of them essentially end, when they are activated, they will end in the common pathway, which ultimately causes the creation of a fibrin clot. And remember, fibrin is an insoluble protein, kind of binds together the platelets, the red cells, the little ends of the damaged tissue, and hopefully forms that actual solid true clot that stops the blood from leaving the area, stops any sort of bleeding that was occurring. So when we look at this, you can see each of these letters and numbers basically represents a protein that has to be functioning correctly in order for it to end in a clot, this whole thing to end in a clot. And you can see that there's a lot of potential for areas that could get messed up. If you have a protein that's non-functional, or if you have something that's in low numbers, just missing one piece of this puzzle essentially means that you can't end in that clot that you want. Now, obviously, we have intrinsic and extrinsic systems, so that means we can trigger it one of two ways. If intrinsic's not working, there is still extrinsic, but there are obviously issues with that too, because if you have an internal intrinsic damage, it's not going to trigger the extrinsic system, and you could potentially have a bleeding event. So all of these numbers here, the tests that we're going to do are kind of looking to see, how might they be affected, or which of these pathways, the intrinsic or extrinsic pathway or the common pathway, is problematic in the formation of the stable fibrin clot. In lab, we talk about the prothrombin time, and the prothrombin time is a test that measures both the extrinsic pathway as well as the common pathway, and it kind of gives you a clue, because these proteins are unique to these two areas, these pathways, gives you a clue of how factors 8, 10, 5, thrombin, and prothrombin are functioning. Are they actually able to work? And so the gist of how this works is you're going to draw citrated blood, or blood into a citrate tube, which is a blue top tube, centrifuge it, get rid of the red cells, and then you add in something that's going to cause creation of a clot. So in this case, because we're talking about the extrinsic pathway, we add in the extrinsic trigger, which is thromboplastin. It's just a protein that comes from damaged cells. It's kind of held in or around cells, and then when they get injured, it gets released. And that, in addition to calcium, actually triggers the proteins that are in that extrinsic pathway to change shape and to become active and to form a clot. And when this happens, you can actually see a change in the plasma. So it goes from clear suspension to a very thick, viscous, almost mucousy kind of clot. And we have ways of measuring when that happens and really how long it takes to happen. That's kind of what we're looking for in the PT or prothrombin time, is how long did it take for this clot, once I added the factors that you need to get it going, how long did it take to happen? Roughly, it's between 11 and 14 seconds. That's normal. If it's elevated, it takes longer. That could be an issue. If it's depressed, that can also be an issue. So we need to measure how long it's going to take from step 1 to clot formation, and it should be, less than 15 seconds. So how you can tell that the clot has happened is by measuring the viscosity or the turbidity change. Now, in lab, we looked at the fibrometer. We may have looked at this already. And what you'll see is this little thing basically just mixes up the plasma and the thromboplastin and calcium, and it mixes and mixes. And once the clot has formed, the little mixing probes stop because they can't move anymore because of the thickness change. Then it stops a timer, and then that tells us, okay, that's how long that clot took to form. There are now sort of turbidimetric ways of doing this. We can, similar to the platelet aggregation study, we can kind of see a change in viscosity, a change in opacity. And so that will help us know if there has been a clot formed or not. We actually have this little one. This is a point of care test, meaning it goes with you to the place where the patient is rather than is done in the lab. And it's pretty simple. Add the same stuff, but we're measuring light passing through the tube instead of the physical presence of these strands of fibrin. It's not stopping a mixing process. It's just changing in turbidity. So this is one way we measure prothrombin time, and remember that this is for an extrinsic and common pathway examination. Now, reporting out a PT time is not quite as straightforward as it might seem. There are different reagents that basically cause different results when you use them, and that throws PT times off a little bit. And so let's say I'm in Houghton, I get my PT done, and it's reading 13.2, and then I have that exact same day, I somehow end up in Denver, and I have my PT done, and it's reading 15.5. Now, they may not actually have been changed. I may not have actually elongated my PT by 2 seconds. What the difference is that here in Houghton, they're using one kind of thromboplastin reagent, and in Denver, they're using something else. And so we needed a way to standardize the PT times across the country and obviously internationally, as you can see here. So we do something called the International Normalized Ratio, and it's just a way of reporting PT results for patients who are on anticoagulant therapy, and this is typically people who get frequent PTs are taking some sort of anticoagulant because they have a clotting issue, and they're constantly having PTs done. And so we want to make sure that the PT done in Houghton is the same as the one, or is comparable to the one done in Hancock, to the one done in Denver, to the one done in Singapore. So it allows for us to have consistency from each lab, physical lab, from here to there. As I said, part of the issue is that different thromboplastin reagents, so like rabbit thromboplastin or human thromboplastin or bovine thromboplastin, will cause different PT results. So we have this equation. It's actually pretty simple. Basically, the INR is the pro time of the patient over the protine of the reference plasma. So basically, you're going to have a control, something along those lines, that you will use as a reference plasma, like a known. And then you see that little ISI, that's going to be something that the manufacturer of the reagent is going to have to tell you. So they have to do this kind of testing to figure out what number their ISI is, their International Sensitivity Index, that applies to their product. And so, rabbit thromboplastin will have its own ISI, human will have another one, bovine will have another one, and it's up to the manufacturer to tell you that. So again, you're taking the pro time of the patient, you actually run it with the patient for the patient, then you compare that to what the reference plasma would be, and then you bring it to the power of the International Sensitivity Index, which would kind of come on like the insert for the thromboplastin reagent. So let's see if you can do this math. I want you to take a second to calculate the INR for a patient whose PT ends up being 23 seconds when it's done in the lab. The normal PT or the reference plasma was about 12 seconds and the ISI was 1.2. So pause here for a second, quick plug and chug and see what you get. Okay, coming back. Now maybe you can see that one of these numbers looks very similar to what you got. If you did the math correctly, it would look something like this: 23 over 12 to the power of 1.2. Remember, you do the 23 over 12 first and then bring it up to the power of 1.2. The INR, which would be the reported result for this patient, is 2.18. So I will give you these numbers. You have to be able to kind of work with them and put them in here, but just know that you don't always just report out the actual length of time that it took. You're going to report the INR because we're trying to standardize things from one place to the next. Pro times, we're measuring the extrinsic and common pathways. So we have to have a way to measure the intrinsic pathway because you might have an issue with one and not the other, and if you only do one test, you'll never find that. So we have what's called the activated partial thromboplastin time, so APTT, which measures the intrinsic and common pathways, and you can see kind of a handful of different factors because these are the ones that are also in intrinsic and common pathways. So the really key difference here is that you add different reagents in. You're still going to use citrated blood, you centrifuge it, you use the plasma. Remember, we have to have plasma, not serum, because plasma has all those proteins floating around in it. And then in this case, we're not going to add thromboplastin because that's a trigger for extrinsic system. We're going to add platelet substitute, something that's kind of like a platelet, and then another sort of generic activator substance that would be similar to what would cause activation of the intrinsic system within the human body. And calcium. Calcium is required for both. So it's a two-step process. You can kind of see here, one of the ways you can tell the difference between intrinsic and extrinsic, the PTT is when the T's are in a relationship, intrinsic, and then the PT is when the T's are not in a relationship, they are X's or extrinsic. Kind of sad, but I think it gets the job done, right? So you'll do this whole thing, and then you'll record clot formation time, and normally this will take a little bit longer. The intrinsic system is a little bit longer. It's about 25 to 40 seconds. You don't have an INR here for this one because the reagents are all pretty much the same no matter where you get them from what I understand. So we don't have to do an INR. You can actually report out like 25 to 40 seconds, the actual time that it took for the clotting to happen within the activated partial thromboplastin time test. So a little similar to ProTime, but remember it's measuring the other branch of that coagulation cascade. And sometimes we want to just know what's happening in the common pathway, and that's where a Thrombin time or Fibrinogen kind of comes in. It really just looks to see how is the Fibrinogen. Is it present? How much do we have? Is it actually working, the stuff that we've got? And so you'll do what's called the Thrombin Time or Fibrinogen assay just to kind of figure out what's up with Fibrinogen. Very similar to the other two, you're going to add thrombin, which is that enzyme that converts fibrinogen to fibrin, to citrated, diluted PPP. Remember, PPP stands for platelet poor plasma. And the reason why we can't have platelets in here is because, as you just saw on the APTT test, platelets are something that actually stimulate the intrinsic pathway. And we don't want to stimulate the intrinsic pathway. All we want to do is get the conversion of fibrinogen to fibrin. So we're taking out things that could potentially cause one of the other pathways to happen. The citrated part is also good because in there what the citrate's going to do is it's going to grab the calcium out of the blood so that you can't activate these pathways because all the calcium's gone. So we're kind of just ensuring that we're measuring what we actually want to measure, which is just fibrinogen, not intrinsic, not extrinsic, but thrombin and fibrinogen, essentially. So you measure the clotting time. How long does it take? I add the thrombin, see how long it takes. We do this via absorbance, turbidimetry, that whole, very similar to what we've seen before. And you'll actually use kind of a standard curve to estimate the fibrinogen levels. So someone has created this curve where if you get an absorbance of a certain level, that means you have a particular amount of fibrinogen present. So it's not just is the fibrinogen there or not, it can kind of give you a clue as to how much you will have. Obviously, the longer it takes the clot to happen, you can see on this picture up at the top, that obviously the less fibrinogen you have, like you have a concentration of 1 milligram per deciliter, it's going to take a way longer time for agglutination to happen or for the clot to happen, like 50 seconds, versus if you follow that x-axis all the way to the right, you can see that, you know, with a concentration of 7 milligrams per deciliter, you should be clotting in 10 seconds. And so we use this to kind of estimate how much fibrinogen do we have based on how long it took to clot, and then we might be using, you know, an absorbance sort of reading to figure out when that clot is officially formed. So it's very similar to what we have seen before, but it's just really taking that little final piece of the pathway and examining it and saying, all right, is the fibrinogen there? How much do we have? And does it work? And those are two really important questions to answer. And finally, we're getting to that fourth component of the not fibrinolytic, but the hemostatic system that we want to look at, which is fibrinolysis. And we want to know that, yeah, everything's great. We are making clots just fine. What if there's a problem with our cleanup crew, our ability to break the clots down and get rid of them when we don't need them anymore? That's where the D-dimer test comes in. So fibrinolysis, as it sounds, is fibrin lysis, basically splitting up fibrin once we've made it and we're done with it. And the enzyme that does fibrinolysis is plasmin. So you can kind of see is plasmin active in doing its job. What happens when plasmin is active is it breaks apart fibrin, and actually fibrin breaks apart into a couple different pieces. There's a piece X, a piece Y, a piece E, and then you'll notice there's a D piece, and this is called the D-dimer. Dimer meaning there's like two parts to it, right? So what we can do is if plasmin is active, and if fibrin is being broken down, then there should be a high level of D-dimer in the area in the bloodstream because the breakdown is happening. So we measure how many D-dimers do you have, or what's the concentration of D-dimer in the blood to give us a clue if we have fibrinolysis happening. And that could be a good or a bad thing. Like maybe you have widespread fibrinolysis and you don't want it. Maybe that's something that is negative and we're going, okay, why is all this happening? Maybe there's clots all over the place that we didn't realize and you have all this breakdown going on and as a result you're releasing a bunch of D-dimers. Or we're wondering, okay, we had this big clot, we gave the person a thrombolytic, something to break it down. Is it working? Is it breaking down? We can check and see if the D-dimers are present. So it's the test to see that the cleanup mechanism is working, and specifically that plasmin, that enzyme, is doing its job. So obviously the more D-dimers you have, the more fibrinolysis is going on or occurring. And there are two ways to kind of measure the levels of D. The Elisa test, which we will talk about in pretty great depth in lab, so I'll just leave it right there. It's an enzyme test essentially, and agglutination. And one tends to be more sensitive than the other, but you could use either one to kind of get those levels of D-dimer accurately measured. So this ends the video. I think that we've accomplished the goals that we had, all of them here. As we go through this in class, feel free to ask questions, shoot me an email, you know how to get a hold of me. If any of these seem kind of fuzzy, we'll be applying these concepts in class.